Hello, everybody, and welcome back. First of all, Happy New Year. After a break from this project, we are back for more. It was a break without videos, but I actually continued doing a few housekeeping items on the project. So let's first of all try to take a look at what was achieved during that. So if I do this and I try to find the the start of that. So most of the work was done to actually enable us to control the caching types for memory, for virtual memory mappings, and that goes through two things. So the page attribute table, the PAT, and then the MTRR. So if we MTRR, and that should be somewhere around here. So yeah, a bit of a problem with MTRR. The thing here is that the implementation is based around hopes and prayers that the UEFI or BIOS firmware has initialized MTRR to something sane, like write back. And what we do here is basically we just get all the initialization that the BIOS or UEFI firmware has done, and we print those. We don't try to do anything. So we just want to make sure that we have something sane to work with. Otherwise, that's pretty much all for MTRR. Then we made a few other changes. So basically, just to get into a few details here, MTRR is an older system that basically allows to define caching for some fixed ranges of page or addresses. And we had, so MTRR has fixed ranges, but also has sort of dynamic or variable ranges that can be set. Except that we are not interested in setting the caching behavior for ranges. We want to have fine-grained control. We want to be able to set it by, or rather on each page. So that's what the PAT here is for. So that's page attribute table. And it's a recent addition that basically aims to replace the MTRR, but it's not that simple because it doesn't replace MTRR. It builds on top of it. So that's why you have this paragraphs of rants here, just so that I can keep it in mind. All right. So that's for this side of things. And when you have PAT enabled, so that's PAT plus MTRR, what it does is it defines sort of entries. So you have 8 entries in the PAT for cache control, and for each entry you decide, so for each slot that they call them, you decide which cache type you want to have, right? Then in your page in attributes, so the bits you set on pages, you have these 3 bits here. So PAT, page cache disable, and page write through. And with these 3 bits, you basically choose which slot you want to be in, and it in turn chooses which cache type you choose for that page, for that particular page. So yeah, that's the idea at least. So you set the PAT with the types that you would like. So that's something I have done here. So that's this part here, the part where you do association between slots and cache types. And then after that, we had to rewrite, so that would be somewhere over here. Yeah, so we had to rewrite pretty much all the cache-in stuff, all the flags and stuff for our virtual page mapping. And that basically translates to this. So this is the table that we've seen before. So with to have write back as cache type, we want path to be 0, cache disable to be 0, and page write through to be 0. So that's what we have here. Same goes for all of the other items there. Right, next would be the flags. So here in flags, I've decoupled the actual flags we set on the page from what we request from the virtual memory mapping system. As you can see here, we now send page size as a page size, so huge, large, or just page, normal, as well as cache control, which is one of the 7 cache types. And here you can see that we only have 6 of those, because on the 7 slots, we have a few that are reused. So this one here, and this one here are all reused. Write back is in here and in here. So effectively, we only have 5 that are actually being used. Right, so that's pretty much all that we have done. And yeah, also a very important thing to note here is that now we have different entry types for different page sizes, because if we go to here we go. So if we go over to here, you can see that the flags in here, depending on the if we use larger pages, so basically for 2 megabyte pages here, we do have this path flag that goes into here, but if we use just 4 KB pages, it goes here. So we needed to change how these are laid out. So that meant that we needed to create entries or pack structures. They all still have the same type, so that's all right, but they have different structures now. And we have this, so I made them so that they all duck type to the same thing. So they all have this set flags, set address and get address thing, set cache control, but this is just internal to here, but yeah, and print, of course. So same goes for large pages and just page entries, which are the normal pages. That also meant that now we needed to start managing pages of larger types. So that meant to basically rewrite this whole, let me just make this a bit bigger. Yeah, so here, a map page, we rewrote this whole write page table here to check if we want to create a huge size. We do the thing with huge size. Otherwise, same for 2 megabyte pages and same for smaller pages. So it means that now our virtual memory mapping allows us to map larger pages. So that means that if we try to allocate a large amount of pages, we should be able to achieve that with writing less, writing less to the page mapping structures. And it also means that the CPU has to cache less entries in the TLB to map the physical pages that we want to access to they're virtual addresses. So that's performance gains pretty much all across the board. Another thing that we now can do is the flags, since we can set the expected caching behavior in the flags now, we can squeeze more performance from things that actually really work well with different cache types. So for example, we have the frame buffer. Ooh, whoops, where did that go? So we have the frame buffer, and the frame buffers usually you write to them more than you read from them. So what you want to have is the CPU to do as little write trips to the actual frame buffer, and you don't want to invalidate any caches on stuff like that. So, or at least as little invalidation as possible. So that means that we need to write to use something like a write combining cache type. So what else have we done here? Oh yeah, so we started work on, so that should still be in x64. Well, what was that? CPU. So here I started work because we needed those for NTRR and BAT, I think. Yeah. So I started doing some work on MSRs. Also added a support for those in. So I think it's x64 assembly that we have read MSR and write MSR in here. Also that take in an entry from the MSR enum and a value, or rather returns a value, and does the thing we expect it to do. So that's pretty much all that was done. And now we are going to go back to where we left off last time. So that goes, and then we go to chapter 12, the APIC. Okay, great. So now we need to write a driver for APIC. And we actually have two forms of APIC. We have the XAPIC and we have the X2 APIC. Difference between the two is, well, X2 APIC has some more advanced features, I'd like to say. But the main difference to us at this point here is that XAPIC uses MMIO, so memory mapped IO, and X2 APIC uses MSRs to basically set and read its registers. So where were we? We were here, and we don't really care about all of that. So we should probably just go over here. I'm just going to jump into the X2 APIC here for a second. So yeah, it uses register address space, and that means that, yeah, it has MSRs, whereas the XAPIC has MMIO offset. So it has the APIC base address, and then from there we offset to different registers from there. Cool, so that's the main difference. We are going to try to write a driver for both. I'm not sure if the conversion of both is straightforward. I'm not sure yet, but we'll see. Okay, fine. So let's now go back to just the regular APIC. We know that they are going to have the same registers, so they should be pretty identical. So yeah, let's get started. Right, so that means that we are going to go here, create apic.seg, probably and have, is this how I want to do this? Not sure. I am not sure. So APIC, and then here I want xAPIC.sig, and then this should go. Cool. Cool. So here we probably should have probably should still have APIC.sig here. And this will so hold on a minute. Yeah, so because the tool that we have created does not go into subfolders, we are just going to create this file here to import xAPIC and x2APIC from. So, okay, it's been a while since I've written Zig, so I might be a bit rusty, so yeah. This one is APIC, xAPIC.zig, that's fine, and then we'll do pretty much the same thing here, and we'll create afterwards. So, no, that's not it. x2APIC.zig. Cool. And here I'm just going to APIC.zig, probably go into here and do reachable. Yeah, probably that does not work. So comp time. Compile error. Where is compile error? Is it in stud something? Yeah, that's not what I needed. Stud is import stud, and this one here would be oh, never mind. Okay, it's been a while. So that's compile error here. Okay. X2 APIC, not yet implemented. Yeah, sure. That sounds like fun. Right. Okay, so you go away. Cool. So go file, and now we can get started. So let's go back here. So we are going to receive, this address here is the typical local APIC address, except that we are not sure that it is the actual address, and we rely on ACPI. So where the hell is it? Yeah, there we go. So local APIC address, that's something what we notify here from our ACPI parsing. So that's something we need to actually get. So we are going to get a public function in it that will take in LAPIC base address, right? And this will be a P address. This is very important. And means that now we need const memory, I think, is import memory, something like memory.zig. Cool. So this one here returns an error or void for now. Not sure we actually care about that. Is this fine? That's fine. Cool. So now that we have our P address, we need to also define all of these offsets, at least the ones that are not registered. Okay, so I have all of them here. Very nice. So we now need to just so var, not public, but just var local APIC base is undefined here, right? Now let's call this fizz. Okay, and we do var lapic, yeah, base is also undefined, but this one here is for memory dot the address. Yeah, this one is memory dot p address. Too many T's there. So right, so physical. This one here is lapic base address. And here we are going to actually need to jump through some hoops. So this is where XAPIC and X2APIC should diverge slightly. Here we need to map this physical page to be, well, first of all, to be virtual, and then second of all, to be uncacheable, because we don't want to. So for correct APIC operation, this address space must be mapped to a memory, to an area of memory that has been designated as strong uncacheable, UC. That means that we, rather, that comes from the fact that we don't want to have writes and reads from APIC to be cached, or from any MMIO interaction actually to be cached. So that's why I needed to actually do the cache control work I had to do before. Right, so here we need to map our virtual memory or physical memory to virtual memory. So the mapping is actually already done for us. So we just need to get the memory map and call physical to vert, phys to vert from memory here. Hold on, phys to. Okay, let me do that again. Phys to vert. So we just need to call this. Now the question is, we need this memory map or page map manager to be passed to us here. Sure, so this would be page map, and this could be memory.page map manager. Not used, okay, that's fine. So const APIC base is page map dot phys to vert of some p address, so that's lapic, or let's just pass it phys p address. It's good. Right, so now we need to actually whoops, there we go. So we can do this actually. Now we need to so what do we need to do actually? We need to remap this. Yeah. So page map dot mremap, remap maybe. Huh. So this is a bit bro. Yeah, because we are in architecture specific stuff, because if we were here, we do have this mremap here. So we have two versions of mremap. One takes a new physical range to map to the virtual range, as well as new flags. The other one just takes new flags and remaps that virtual range to those new flags. And this allows us to basically, if we have something that's mapped in 4K chunks, to move that to 2 megabytes or 1 gig mappings. So it's all nice. Okay, good. So here remap, we want a virtual range. So that would be start is I guess APIC base. Length is, I actually have no idea here about the length, so, but I'm assuming just 1 page. Yeah, to a 4 kilobyte region, so just 1 page, I guess. So that means that we need constant dot, so constant is import constants.sig. So this one is default page size. Okay. And I guess we have an optional type to pass. I'm gonna need to recheck if the type is optional. Yeah, it is optional. Cool. So that's nice. And then here we need to pass in flags. So here I think we can do this dot flags, default flags, and I've added this mechanic here. It's called extend. That takes basically a struct, and it extends the default flags with the extend flags. So one of the things we need to set is read write, because now it doesn't default to write anymore. So it defaults to read execute. Let me just double check that. Yeah, it defaults to read execute. Hold on a minute. Yeah. So that's one of the things that changed. Then here we have cache control. We want uncacheable. And what else do we want? I guess that's pretty much it for now. This needs to be tried, and it is void, so that's fine. So that looks pretty good. So now what do we do next? So actually I want to have a sort of, yeah, let's think about how we want this to be. Pretty much all the registers here are some sort of 32-bit registers. Except that we actually want them to, some of them we want to behave differently. So for example, ASR, TMR and stuff like that. I do not want to expose all 7 fields through some simple read and write functions. I actually want to have specific functions to handle this, all of them. So I'm not sure how, or I'm not sure at which level we are going to create our abstraction now. But I guess we are going to see. Fine. So let's now try to do a few things here. Now that we have initialized our APIC, let's actually try to log some things to trace. So this won't be, I guess we need stud. There you go. So stud.log.scoped. And let's call this xAPIC. Should we call this something else? No, that's fine. So log.info initializing XAPIC. Yeah, that's pretty much it. So just so we know, base, and this should be something like, yeah, that looks pretty good. So this is APIC base address. Mapped XAPIC base to something like this, and this one will be that dot to address. Of course, this one returns U64. It does. Right, fine. Now that we have remapped this, we can actually start reading from it. So let's actually read from it. So we want log.info. So XAPIC ID is some sort of this, and I guess this is a good point to introduce a function to read register takes in I guess a comp time int offset and returns an error. No error. Turns in a U32. So this one would go const register address is APIC base .to address plus offset. Hopefully this does not cause problems. So now we have an address. So const register pointer is at pointer from int of register address, and we probably need to this is a pointer to a U32. So okay, and here we return register pointer dot whatever the value under that is. Cool. So hold on a minute. There we go. So here we need to do const ID is read register. What do we call it? ID. There we go. Whoops. Yeah, okay. Register. Version register. Sure. Whoops. Yeah, register. Sure. I don't really care. Do you think I care? I don't. Register, and this goes there too. Sure. We are going to need to make that much better, but for now, we are going to go with this. We do the same for, hold on, let me just do this and do ID comes version. What is this? What is going on? So ID becomes version. There we go. Cool. No. Yeah, of course. So not that language. All right, fine. So now we want to probably, so I'm looking at this remap here, and it actually does sound, oh, actually it does look very bad. It does look very bad for the very simple reason that we need to actually pass it like we need to actually pass it the physical range, not the virtual range. So what am I going on here? Right, so what we need is actually not a remap per se. So basically, let me just go back to the actual virtual memory manager here. Can I find a remap, please? No. Maybe, hold on a minute. Yeah, this is not what I wanted to go. This is where I wanted to go. So this first remap here just calls mmap, but with this remap true parameter here. And then this one here actually calls remap for that virtual range. So that's what we want to go with, I think. So mmap, that means that here the first argument now is going to become a physical range. This one is a virtual range, and then this third and final argument should be remap is true. Okay. Right. So here we have another small problem. Why did I forget this? Not sure. Who can tell? So here, start is APIC base address. Cool. Length is well, constants dot default page size, and here we need to specify a type. So this type would be API. I mean, sure. All right. So that does it, or I'm not sure. So physical range, virtual range, flags, and then mmap args. So flags, and then mmap args. Ooh, okay, I see it. So this is not where it's supposed to be. This is where it's supposed to be. Remap is true. Cool. Let's get that there. Very nice. Okay, so that looks quite a bit better, I think. So maybe we go to kernel main and we try to use that somewhere. Right. How do we go about this? Actually, let's not go to kernel main. We have SMP init here. And so once this thing here is done, we should have all the data actually available to us. So that means that we can come over here, do something like APIC is import Const arc is at import arc because I don't want to fight this. And we can probably do something like this and just replace it with arc. And then here would be arc APIC. Looks good. Looks good, except that now we have... All right. How about this? That looks pretty okay. Not really, but okay, fine. So, .xAPIC .init with lapic address and mem dot, so we need mem memory.seg, probably mem dot kernel vmem. That's our yeah, we actually need to build this. So yeah, make -b all. Source file arc has no member APIC. Are you sure about that? Oh yeah, we need to regenerate that, don't we? So cd kernel, and then we do zig build gen arc. How about now? Why? Maybe if we maybe zig cache, something like that. Can we actually force it to do something? Yeah, okay, fine. That did the trick. So let's go back here and do where is it? There we go. Cool. So now we do have a valid error message. We should be here. Right, so SMP 44 expected memory type manager found vmem. Right, okay. Yeah, so this one is virtual allocator, not well, that's bad. And that's not even a pointer, so right. Hold on a minute. Let me check something. So vmem virtual allocator. And this one is okay. So it's defined in here. Okay, that's kind of bad. So what we want is this platform virtual mapper is what we want. Except that I don't really like exposing this. There should be no problem doing this. Hopefully. Okay. I guess it works. Not what I want to do. Just split this here and go for this. Let's see if we are going to be able to. Oh, would you look at that? It actually did work. Right, so we have ID 0 and version 5.0014. Not sure about that, so let's see what we should expect from those. There we go. So ID is yeah, because we are the bootstrap processor, so we should have ID 0. And here is another difference between xAPIC and x2APIC. So for XAPIC, we should have about 1 or 7, 8 bits to encode the APIC ID. So we need to shift left that value that we received by 24 to get the actual ID. In X2 APIC mode, we can actually use the full size of the 32-bit register to encode the ID. That means a lot more IDs. So here we have a maximum of 256 CPUs with unique IDs. And here we have quite a few more. So that's good. So do we have version somewhere here? Just want to check that what we got is actually valid. There we go. So version here. Version numbers. So first byte here has so anything from 10 hex to 15 hex is an integrated APIC. Otherwise, single digits in hex are discrete. And what did we get? We got 14. So that's integrated APIC. Cool. And then we have next byte is reserved, and then here we have max LVT entry and support for AY broadcast suppression. So this is the LVT entry is -1, and we have 5. So we have 6 LVT entries here. Okay, cool. And this one we don't have. Very nice. So now we can actually do read and write from the XAPIC. So one thing we need to do is actually, hold on a minute. In this code here, we want, do we have CPU? We have CPU, we do have CPU. CPU.has feature, X2 APIC. Of course, this needs to be an if statement here. Yeah, okay. So if CPU has that, we do try apic.x2 apic.init with lapic. I guess we don't really need lapic address here anymore, since we are just going to I'm not sure how it goes for MSRs. Where is that? There we go. And of course, we need to go ahead and enable that APIC. We still haven't done that, but we are going to get there. So okay, so there are a few exceptions, but otherwise we just call read MSR, write MSR with the actual address, and that should be okay. Cool. So this one here just needs an init. There's no things that get passed to it. Else if, do we need to check for has feature APIC or XAPIC? No. I guess we don't need the if there. We can just assume that we have one. Very nice. So let's see here if our CPU is going to. Oh, of course. So where was that? There we go. Not yet implemented. That's very good, actually. Forgot about that. Right, so Sure. Okay, so how about this? Expect 2 arguments, of course. And we do actually just support just the APIC, so we still go through our initialization code here. Very nice. Cool, so now let's actually go back to here. And we should probably just enable it. I'm not sure if we need some enable disable functions, but I think we should just enable it, just point blank. All right, so here we go. So presence, we already know for that. Hold on a minute. Okay, so I guess we should also do this check here. Bit 9 of EAX. So I'm just going to check. So features. There we go. So APIC. Bit 9 of EDX. Is that what they said? Operand of 1. Oh yeah, of EDX. Presence if set, absence if clear. Okay. So that means that this is so we need to do something like if not CPU dot has feature APIC. So log dot error CPU has no APIC. I guess this is not where it should go. Yeah, this is not where it should go. It should probably go in CPU.init. So in CPU.init here, we fill in the data that we want, but we need to also do checks on the features that we expect. So we can abort the boot process fairly early. Right, so how do we go about this? Do CPU checks. Sure. Do CPU checks. And then this one returns a void or yeah, sure. Can do that. So if CPU has, or rather if has feature APIC, or if not has feature APIC, return error dot no APIC. And that would be our first check. And if we ever don't have an APIC on a machine, we're just gonna print an error and move on. Just want to check that this doesn't happen to us. No, it doesn't. Of course, it doesn't, because we have one. Right, so now let's go back to initializing this thing here. Right, so init, go back to this. MSR, not interested, actually. Or we have, wait, hold on. Do we need to go through the MSR? Not sure we need to go through the MSR though. They say in either of two ways. I mean that we can, I think that means that we can choose. But here they also reference the MSR. Okay, so I guess we need to go through the MSR then. Cool, very nice. So we need the APIC base MSR 1B. I think I've already added that to my list of MSRs. If it's 0, then yeah, it's disabled. So we need to set that to 1. I think just give me the, there we go. So this is the physical address. We don't really care about that. Global enable and disable. So bit 11 of this MSR here is what we need to do. So we are going to enable this by doing const, or rather var. What is that called? APIC base. Sure. APIC base is, I guess we need assembly. Oops. So const assembly is import assembly.sig. Cool. So read MSR, and that one would be APIC base. Cool. And then we get APIC base, and we set yeah, we OR it with 1 shifted left by 11 to set the 11th bit, so this one here, and that would enable it. So we need to just write back. So assembly dot write MSR, and that would be APIC base with the value of APIC base. Does this need to be tried? No, it should be all right. And of course here we need to do log.info xAPIC enabled. So hold on a minute. Yeah, let's do something like this, APIC base, and then we, because it might already be enabled by the BIOS or firmware. So I'm just trying to see if we, of course, it's been a while. Okay, let's see now. Status of this is 9, and 9 is so that's 1 1. And if I go here, why is this a 9? Oh yeah, because this one here is set. BSP is set and 11 is set. So it was already enabled actually. So that's fine. I guess, yep, so that's fine. So xAPIC is enabled. We are happy to go our merry way. Now, should we how should we go about this? Because we want to use this driver, this local APIC driver, to initialize all the registers and interrupt controllers and stuff like that, maybe the timer. So we probably need, for the timer, we probably need a special driver to handle all the different modes and stuff like that. For the interrupt control, we might want to actually have a different control also to handle those. So yeah, I'm not sure about the design state that we have put ourselves in, but it actually does work, and that's very important. That's the most important thing there is. Also, the local APIC, we want to use it for a few things. So our use cases. So for use case number 1 is probably interrupts and stuff like that, right? Number 2 would be IPC, so interprocessor communications. And number 3 would probably be something like timer, right? And I guess we could do 1.5 here, would be AP wake up. So these are the things we want to do. So interrupts, we want to be able to route different interrupts to different CPU cores to handle them. We want to also be able to use those interrupts to load balance, or rather, we want to load balance the interrupts so that we can have the CPUs that are the freest handle the most interrupts, and we need to adapt that balance in our scheduling code. And then we have AP wake up. This is something we are going to just do once, and once the APs are awake, we don't really need to do much more. But actually, I think I can just delete that, because AP wake up will just use the same mechanics as IPC. So IPC is message passing between cores. This is very important. For example, if we ever need to change a page map, or if we ever need to change a page map, we are required by the Intel SDM to synchronize all the cores to do the same page map changes at the same time. Same if we want to apply changes to cache-in behavior and stuff like that while we are running on all cores. We need to do that on all cores, so that's something we need IPC for. Timer, self-explanatory, I think. So these are the 3 things we need to design around, and anything else would just be nice addition to this. Alright, well, this is a good point to stop for today. So we still need to do a few things before we call this done. So we have interrupts, IPI, and timer for the XAPIC, and then we probably need to do the same for X2 APIC. But I guess this should be let's mark it as optional for now. Yeah. So next time, hopefully, we are going to start working on interrupts. This should be fairly simple, and we should be able to test them by just rigging some timer interrupts and having them go off. With the brand new year comes a brand new resolution to make progress and great strides in this project. So if you don't want to miss anything, hit like, subscribe, maybe tell a friend. I'll see you in the next one. Happy New Year!